Massimiliano, and I work at the PFL in Lausanne in a group named CETAS that manages the HPC clusters for the entire university. And my main duty there is to take care of the automation of software deployment. And that led me to be a core contributor of a tool that I'm going to present right now, Spack, a package manager for scientific software. So this will be an introductory talk to this tool. I will give you some motivation. Why do we need such a tool? And really a bird's eye view of what it is, how it works with the community that started gathering around it. I will touch three aspects that I think are peculiar of this package manager. And finally, I will tell you what is to be expected in the short to mid-term in terms of big features that will be added to the tool. So let's start. Why do we need something like that? Why did the project start? Well, basically the project started because scientific software is inherently complex. Here you see a visual representation of a widely known finite element library, DL2, the blue node, along with its dependencies, the red nodes. And you can figure out that if a scientist or a dedicated person need to go through building and installing all the dependencies in order to start using this finite element library for his work, well, it can be cumbersome, it can take a lot of time. And furthermore, if you take my point of view, that of a person that has to support an entire facility, you don't have to deal with just one application. You have to deal with a number of applications, a number of libraries for your users. Those libraries usually need to be configured in many different ways, and those different configurations need to live alongside each other. If you have an heterogeneous cluster, you need to build the same application for different backends, maybe with different compilers, and this gives rise to a combinatorial explosion of the software deployments that you actually need to do. So what was the common practice since a few years ago was to go manually or almost manually through all of that, and you had dedicated teams doing this kind of work. But clearly, this is not an option anymore. And in particular for me, I would tell you my experience, this was particularly frustrating because if you abandon all the requests that are proper to the HPC world, like having the executable that is tuned for the bare metal or having multiple configurations of the same software installed at the same time, well, you can go to usual package manager and there you have the same thing happening in a snap. Like you need a software, you don't have it here, you just tell the package manager to install it and then you can use it. And the claim is that scientific software should be that easy to be used. So what is Spack then? Spack is basically that missing package manager for scientific software. Using it is fairly simple. You just have to clone a Git repository if you want to use the bleeding edge, or just extract a tarball if you want a tagged release. You source a setup file, which basically brings the executable into your path. And then you can start using it like any other package manager. Spack install HDF5 will basically download, configure, build, and install HDF5 along with all of its dependencies. Here for your later reference, you'll find a link to the home page of Spack. I was saying, who can profit from this tool? I would say 4 categories of users. First of all, end users of HPC systems. People that just have access to an HPC cluster and they want to build a particular application in their home for their own use. They can just download the software and do that. Then HPC application teams. People that want to build a set of application because maybe their department is developing that in as many configurations as possible, maybe in a CI framework, they can use Spack to do that in an automated way. Package developers, just people that just want to distribute application, they could package software into Spack and distribute them to other people. And finally, people like me that need to support a complete deployment at a site. Regarding the recipes, those are nothing but simple Python classes. So we resorted to use Python to have, let's say, a small domain-specific language for the packages. This should be fairly intuitive. In this case, you see an example for a software named Kripke. There are a few mandatory fields, home page and URL. You can set versions with their checksums. You can set different configurations, we call them variant, which will be or not activated during the installation, and of course you can set dependencies. But the main point is you can write simple Python code to describe what is the combinatorial space that is proper of a particular package. We also try to make it easy to work with packages, so we provide a lot of commands to support the creation of either a non-existing package or editing existing packages to improve the recipes or even scrape for new versions of an existing package. And regarding how Spack is developed, Spack is a community project nowadays and it's open source. Its development started in 2013 by Todd Gamblin, who's the lead developer from Lawrence Livermore National Laboratories. And the code base is hosted on GitHub. We have a very large, and I would say engaging community. And just to give you an example, last year, we changed our license from the previous LGPL to a dual license, Apache 2 or MIT. And to do that, we had to ask hundreds of contributors permission to change the license, and we were able to do that in less than 1 month. So the community is there, it's contributing, and I would say it's also very welcoming if you want to come on board. Spack is already used worldwide and in production. Probably the most noticeable thing I can say right now is that it has been selected as the tool to deploy software in the exascale computing project. It's been used at top-level facilities and also at smaller facilities like ours in the US, in Europe, in Australia, in Asia. And, well, this is just to show you the number of hits we get over one random month for our documentation, and they really come from all around the world. And to reinforce the idea that this is a community project, I want to show you briefly the line of code over time just for package recipes. These are like disaggregated by organization, and as you can see, Livermore is not even the first contributor in terms of lines of code in packages, in recipes anymore. So again, Spack is committed to be open source, will stay open source. And finally, there are a lot of ongoing efforts in the community to disseminate best practice. So besides talk, like this one, we are giving full-day tutorials at supercomputing since like 2016. I think that the folks at Livermore gave a full-day tutorial in an exascale computing meeting beginning of year. They will be giving another one in Japan because I hope I'm not wrong on that, but I think that Spack will be the way software will be deployed on post-K machine. And finally, we will have an half-day tutorial at ISC if anybody is interested. So long for like how Spack is organized. Let's go back to a few relevant technical points. I said that one of the aim of this package manager was to handle the combinatorial explosion of software installation. So how do we do that? If I have to summarize it with one sentence, I would say that Spack fights combinatorics with combinatorics. And by that I mean that it combines three technical choices into one coherent design that makes it feasible to manage this combinatorial space. So the first technical aspect that allows that is user-facing. It's a small language that we call Spack syntax that a user can employ on the command line to describe his needs. So you can see that when you install a software, you can specify with an add the version you want. You can specify with a % the compiler you want to use. You can activate or not variants, meaning different configurations of the software that is going to be compiled and installed. You can inject compiler flags or select the backend. And finally, a thing that I didn't show here, with a caret, this language becomes recursive. So you can do exactly the same thing on a dependency of the software that you want to install. So for instance, you could say, I want to install HDF5 with zlib with that characteristics. And that's the first part of the three, let's say, technical decisions. The Spack syntax that permits a user to go as far, let's say, as deep as he needs to specify the configuration options for a single installation. The other part is on the packager side. When you write a package, you will use directives to model allowed configurations, and those directives builds up the combinatorial space, let's say, in a product way. So here, for instance, you have two versions, and you have two Boolean variants, and this already gives 8 different combinations in which you can install this package. And by keeping the various subspaces separated, we make it manageable to have a single recipe that describes all the way in which the software can be configured. As an aside, we also have directives. Of course, I won't go through all the directives one can use. I'll just try to give the basics. But as an aside, we have directives to invalidate, if it makes sense to warn users, entire subspaces of this combinatorial space. So for instance, in this case, this conflict directive basically says that OpenBLAS can't be installed with Intel at version 16 in this version range. Finally, there is one core part of the framework, which is called the concretizer, that takes as input, on the one side, the user request, on the other side, the recipes, where it can check the constraints he has on packages, and fills in the blank. Because normally a user is interested only in a few details and doesn't specify the full set, of course, of details that are needed to identify a single installation. That's the duty of a concretizer, to go through that and fill in all the missing details. What you get as output is basically a graph representation of the configuration you're going to install with metadata on both nodes and edges. And once you have that, you can give a unique ID to that configuration or an hash, and that identifies uniquely what you are going to install. And we use that hash in the Spack store to distinguish among different configurations, for instance, of the same software. So to recap, how do we manage the combinatorial explosion? We have a powerful syntax that is user-facing. We use directive to build up the combinatorial space by, let's say, its components. And we have the concretizer, which is basically a SAT solver for all these constraints that fills in the blank. And in the end, we can come up with a fully concrete graph that can be installed. So another aspect that I think is peculiar to Spack, at least if compared to some competitors, is that Spack has been designed with reproducibility in mind, meaning we try to keep around as much metadata as possible. Whenever you install something, all the information about what is installed goes into a central database. You see the usual path of a database here. The database is basically a JSON file that contains information on what you install at this moment. And you have information like, was this explicitly asked by the user? When was it installed? What is the hash? And things like that. And besides that, inside each installation prefix, we have a directory, .spack, where we keep all the provenance information for that software. So in the example shown in the slide, which is the usual HDF5, we have, for instance, the config.log that has been saved from the configuration time. We have a dump of the environment during the build and a dump of the output during the build. We have all the recipes that have been used to build this software and a YAML representation of a concrete graph for the configuration that has been installed. The central JSON database can be regenerated from the distributed information inside each prefix of the software that has been installed. So in case it gets corrupted for any reason, you could regenerate it, just to let you know. And on top of this, let's say, database of this storing metadata, we have built a lot of useful tools. For instance, we can ask the package manager, what will be installed if I use a particular formula? If I give this formula, I get the output of a concretizer flattened here, and whatever is already installed will be marked. So you know beforehand what you will rebuild or what you will not rebuild due to the formula you use. Another thing we can do is to query what we installed, starting from very simple queries like, did I install zlib? In how many versions did I install it? To more complicated one. You can ask questions like, which software did I install with GCC 8? Which software that depends on MPICH at this version do I have installed? Which software I have installed since a month ago, or things like that. And you can make the same queries even for uninstalling stuff. So that this is kind of useful if you manage software, if you want to wipe out entire parts of it, or you want to know why something is different from something else, you can query it. And finally, which is kind of important for HPC sites, we can generate different kind of module files, from flat TCOL module files to hierarchical Lua module files. These are all highly customizable via a YAML file. As I said, everything is customizable in Spack, ultimately by tweaking some YAML configuration file. And I won't go into the details of what you can do with that. There is a tutorial linked here, which takes, I think, an hour something to go through. But just to give you an idea, we generate module files from templates, as in using a template engine, Jinja 2, and the degree of customization, if you need it, is so fine that it can go to override or extend the entire template file just for a couple of applications if you select them correctly. So finally, which is kind of new feature from November. Spack permits to set up specific purpose environments. We got this new feature in November. You can think of it as Python virtual environments, but just for anything. And to be fair, I think that this feature hasn't been developed so far to its full potential. The idea is that either by using some subcommons as an helper, or by editing directly a file called spack.yaml, you can write all your abstract requests for the software that you need for a specific purpose. And you can override the general configuration for anything else. But, well, if you want details about that, please reach out to me later. The idea is that once you have the abstract request, like I want to install HDF5 without MPI, Python and MPI-CH, then you can distribute this file with anything. It doesn't need to live within Spack. It's just handled by Spack. And the idea is that on top of that, we could start building tools for developers, in particular for developers in the HPC field. If they start saying what are their requirements to develop an application in some particular configuration, they could just ship a spack.yaml file, and people that want to try that out or modify the application or develop it further would just set up the environment, go in using that file and saying Spack install. At that point, following like mechanism that have been pioneered by other package managers like Bundler, Spack will concretize the abstract request. It will produce a log file called spack.log with all the information on what's been installed right now, and you can use both the manifest file, there's spack.yaml, which came with whatever, or the log file to reproduce the environment, depending on whether you want to reproduce the logical environment or the exit one that you installed right now. And yeah, as I was saying, there will be a fully concretized file containing the complete configuration of what you installed right now. So, going ahead, what are the next big things that are to be expected in the roadmap? Well, the first one is CI infrastructure for source and binary packages. People are already working on that. Up to down, Spack has support to package binary artifacts and sign them. But we have no infrastructure to distribute them, let's say, from some central mirror or repository. What we would like to have is, on one side, getting source archives during continuous integration runs whenever a new version is added, so that we can have, let's say, a fallback mirror for sources when we want to build things in case the primary mirror goes down. That happens, and yeah, it's kind of annoying. But more important, we would like to hook GitLab CI runners to run either unusual architecture, which are represented in the figure by Amazon Web Services, or that's like I would say the best feature, or on top-level machines like on Cray machines. People at Livermore are working with a company on Xpoint to modify the GitLab CI runner so that it can set UID, enter the queue, build some software, package it in binary, and then upload it to some binary mirror. What would be the effect? The effect is that the next user that needs the exact same configuration as you, and of course we would do that for common configurations, not like for the entire combinatorial space for every configuration, the next user that needs the same configuration don't have to go through hours of builds. It will just download a binary that somebody else trusted has produced and use that. For HPC, with a binary that is tuned for the architecture, is on right now. So that's the first big thing. The second one, we are trying to design a YAML format to describe the installations of an entire stack at an HPC facility. Basically, an intuitive way to describe all the cross-product that a facility might need to install all of its software. And the idea is that then you could share this file with other facility, and you can even deploy things with a single command. Another one that is ongoing right now, we merged the first bits of that last week, is what we call Spack chain. So this needs maybe a bit of explanation. I told you that we have this central JSON database of the software we installed, and I told you that Spack doesn't need root access to install stuff. It installs basically in its own store that is somewhere. So what if you could download your instance of Spack and register somebody else's instance as an upstream, read-only upstream? And whenever you build software, if it is already present in the upstream, you just use that one. That's basically what Spack chain do. And the usage we foresee is mainly at HPC facility. If you think of that, you can have people like me administering the facility for everybody, for every kind of user, just install the software that is widely used by everybody. And then we could have departments which are interested in some software, install on top of what we do software for their own user, and that can go down to the single user of those departments that need to do something really experimental or need that very weird configuration that can register as upstream a chain of other installations and just install whatever is missing. Well, and it's Spack all the way down, of course. This one is kind of easy to tell instead. Python lacks, I would say, a decent module to auto-detect target information. So up to now, auto-detect in a fine way the target architecture you're on. So up to now, this is done either manually, or if people have just one kind of target, they resort tagging it in a very generic way, like x86-64. What we would like to do is to improve the auto-detection of targets so that we can automatically activate certain optimizations on them. And finally, this is probably the most wanted feature in Spack. We want to improve a lot the concretizer. Right now, we have an heuristics to do all the SAT solve for the constraints. What we want to do is to basically, that seems simple said like that, but basically move to a full SAT solve so that we can instruct the concretizer to prefer to download binaries from mirrors if they are already there, or to reuse software that has been already installed if it doesn't conflict with whatever the user asked for explicitly. Right now, in some way, there are times in which you need to help the concretizer, so you have to over-specify maybe a bit your own specifications in order to reuse software. So that's it for the quick overview of Spack. Thanks for listening, and if you have questions, please throw them at me.